Okay, thank you very much for the introduction. So I'm very happy to have the possibility to speak here on sequences of sets over finite abelian groups and weighted zero-sum sequences on joint work with two of my students and a colleague. And so the general structure of the talk is that I will make remarks about the structures that will be considered, and then I will talk about some arithmetic results for the weighted zero-sum problems. So what are zero-sum sequences? So for a abelian group, generally finite abelian groups, so in this talk we only will consider finite abelian groups. A sequence of elements from the group is called a zero-sum sequence when the sum of the elements is equal to 0. And if one has two zero-sum sequences, then also their concatenation will be a zero-sum sequence, and thus zero-sum sequences form a monoid. And one can study the arithmetic of these monoids, and there are plenty of contributions to the subject arithmetic of monoid of zero-sum sequences. And usually in this context, one identifies sequences that only differ by the ordering of the terms. So sequence is not an ordered sequence, but an unordered sequence. If not, the question of decomposing these sequences and so to study the arithmetic of factorizations would not make that much sense. So in other words, the sequences are in fact elements of the free monoid over the group, or one could also say multiset. So we allow repetition, but do not care about the ordering of the terms. So these are zero-sum sequences. And what about these zero-sum sequences of sets? So in this context, the idea would be to replace the elements Gi by subsets Ai of G, and the usual addition by set addition. So I will come back to this in more detail and also give some motivation why one would want to do this. I will also come to the weighted problems, what this means precisely, but roughly speaking, it means that when it will be allowed to put some coefficients here. So now more formally, what is a monoid of zero-sum sequences? We take a finite abelian group, and maybe we consider just the subset G0 of G. And the sequence of S over this subset G0 is an element of the free abelian monoid with basis G0. So it's common to use multiplicative notation for these sequences. So we write them as formal products. We repeat the elements, or we use exponents to indicate the multiplicity, and then the sum of the sequence is just the sum of the terms. And the monoid of zero-sum sequences over G0 is defined as this set, so the set of all sequences whose sum is 0. And now, I said we want to study the arithmetic of this monoid. So what could this mean? One thing one tries to do is, so one has a monoid, so I assume monoids are commutative and cancellative, and then one can try to decompose elements as one decomposes natural numbers into prime numbers. So one decomposes sequences in smaller building blocks, and at some point this will stop, and if one cannot decompose anymore, then one calls the element then an atom, and then one has a factorization of an arbitrary element as a product of atoms, so irreducible elements, and the number of vectors is called the length. And in general, for arbitrary monoids, contrary to the situation for integers, that's not unique, and so one can consider an entire set of lengths attached to this sequence, to this element. And then the system of sets of lengths is just a collection of all these sets. And in full generality, these sets of lengths could be infinite, but in our case, they will always be finite sets. So in some sense, one goal one can have is given some monoid, one wants to understand these sets of lengths. For instance, for the monoid, it could be this monoid of zero-sum sequences over some given group. And why would one specifically be interested in these monoids of zero-sum sequences? Well, in some sense, they're an object which is interesting, but also, I mean, the historic motivation was that they allow to model phenomena of arithmetic of more classical monoids and domains, in particular, those arising in algebraic number series, so rings of algebraic integers. And the method is that given some other monoid, one can often transfer arithmetic problems to more simple monoid, and transfer has a technical meaning. So it means the existence of a so-called transfer homomorphism, which is a homomorphism of monoids that satisfies certain properties. So for the sake of completeness, I give the properties here, but I mean, maybe it's not crucial. Just let's retain this information. So if there's a transfer homomorphism, then sets of lengths are preserved. So the idea is, so there are monoids one cares about, and one can go to monoids of zero-sum sequences to understand them. So in particular, results on so-called cruel monoids can be proved by transferring the arithmetic problem to an auxiliary monoid, the monoid of zero-sum sequences, over the class group. As just said, these preserve sets of lengths. So if one cares about lengths of factorization in these structures, one wants to understand monoids of zero-sum sequences. And I mentioned here only commutative structures, but even in non-commutative cases, it can be the case that it's possible to transfer to monoid of zero-sum sequences of a commutative group. And this was first noted by Daniel Smiatnik several years ago. So I mentioned the term cruel monoid. So what's a cruel monoid? In some sense, it's an object where one can understand the arithmetic via an attached free monoid. So it's a monoid where the arithmetic comes in a natural way from the restriction of the arithmetic of a free and thus unique factorization monoid. The formal definition is given here. So one has a monoid and one has a map called a divisor homomorphism into a free monoid where one has unique factorization. And what's a divisor homomorphism? It's a monoid homomorphism which has this property. So A divides B in this monoid H if and only if phi A divides phi B. Of course, one implication is just the property of a monoid homomorphism, more or less, but the converse is interesting, because and which gives the special property to this divisor homomorphism. So you see, if I have one monoid and then I embed it into a larger monoid, I could have more divisibility relations, and the condition is precisely that this does not happen. And once one has this, then one can have a minimal free monoid in a certain sense and calls it the divisor theory, and then can define a class group attached to, and so on. And then as said, for the cruel monoid, lengths just depend on this class group and the subset of classes containing primes. And one has a transfer homomorphism, in this case called block homomorphism, which is defined like this. And it's given like for an element, I map it to the class of prime ideals, the classes of prime ideals that occur in the factorization, or prime divisors that occur in the image of this map. So a classical example, and this is in some sense all one needs to know, just recall briefly the general theory. So would be from number series. So give me a number field with class group G. There's a transfer homomorphism beta from the multiplicative monoid of the ring of algebraic integers to the monoid of zero-sum sequences over the class group of K. And it's given by mapping an element to the sequence of classes of prime ideals that occur in the factorization of the principal ideal generated by this element. And what's crucial here is that this factorization into prime ideals is classically known, is essentially unique. So unique up ordering of the terms. So that's actually well defined. So with this at hand, one could ask related questions. So maybe if we have this ring of algebraic integers, one has a norm map that goes to the integers, and then the set of all norms of algebraic integers of this ring of algebraic integers forms the submonoid of the multiplicative submonoid of the positive integers, and one could want to study the arithmetic of this submonoid. Maybe it's interesting. How could one understand it? Maybe it's the same, or that of okay, or different, or in any case, it seems like a natural question. And one might want to exploit, in this case again, that one has a uniqueness of factorization into prime numbers and also prime ideals for the various structures. But there's a certain complication in this process, in that different prime ideals of OK can have the same norm. And then things start to become a bit more complicated. And to treat this problem, one needs so-called weighted zero-sum sequences, not just zero-sum sequences as we saw them, but one introduces weights. And this was initially noted by Walter Koch some years ago. And so what are these weighted zero-sum sequences? So if we have again, as we had it, a finite abelian group, a subset, and now we have a set of weights. I do not yet say what these weights actually are, but I will say so in a moment. And then we have a sequence as before. Then any elements of the form sum omega I gi, where these omega i's are weights, is called an omega weighted sum of S. So what do we take for these sets of weights? Well, one possibility, I mean, what do we need? We need that these weights can somehow interact with the elements of the group. So we just could take integers. So then we could take an element twice or 3 times instead of just once, add a negative sign or something like this. But we also could do something slightly more general. So multiplication by an integer induces an endomorphism on the group. So we just could also take whatever endomorphism. So instead of considering the weight 3, we say, well, 3, this is the multiplication endomorphism by 3. And then instead of just considering those endomorphisms, why not consider whatever endomorphism on the group? And then omega I gi is the image of gi under this endomorphism. One can even go a step further and consider not endomorphism of the group, but homomorphisms to another group, but we won't use this here. And then one has can define, as beforehand, one had sigma of S, the sum of all the elements of S. One can now write sigma omega of S as the set of all the elements which can be written as such a weighted sum. And then one says that S is an omega weighted zero-sum sequence if here the definition is cut off. What one says, it is an omega weighted zero-sum sequence if 0 is an omega weighted sum. So this is a set, and then it would be 0 has to be an element here. So excuse me for this. So so if I can choose weights such that this becomes 0, then I say it's a omega weighted zero-sum sequence. Of course, for other choices of weights, the sum might not be 0. So there just needs to be one choice. And something which is important to note is that, in fact, so the sum is weighted and not the sequence. So the sequence is just the usual sequence, but then the sums of it. And so there are plenty of papers on weighted zero-sum constants. So this was something which was more or less introduced by Adhikari, and then a lot of investigations followed in recent years. And so one can study so-called Davenport constant with weights and ask a question: what is the smallest integer L such that each sequence S over G of length L has a subsequence that is an omega weighted zero-sum sequence, for instance? So one can study Erdős-Ginzburg-Ziff constants with weights what is the smallest integer L such that each sequence S over J of length L has a subset of length equal to the exponent that is an omega weighted zero-sum sequence and so on. So these problems exist without weights, and we can study them with weights. But in this talk, we do something slightly different. So we rather study the arithmetic of this monoid of omega weighted zero-sum sequences. So we don't do zero-sum constants, but more arithmetic of these monoids. And so here's the definition correctly. So the monoid of omega weighted zero-sum sequences, these are all sequences over G0 such that 0 is an omega weighted sum. That's the wrong direction. So, and this is a submonoid of this free monoid, because the sequences have no weight, so it's just usual sequence. And I'm just looking at the time, and it's a bit small, so I have to move. And so it's easy to see that the concatenation of two sequences with 0 as an omega weighted sum has again 0 as an omega weighted sum, and so this is a submonoid, which is in fact larger than the monoid of usual zero-sum sequence. And now, having this at hand, one can show that for K, a Galois number field with Galois group omega, not omega, gamma, excuse me, and class group G, there is a transfer homomorphism from this monoid of norms to this structure of omega of gamma weighted zero-sum sequences over the class group. So here one has to recall that the class group acts in a natural way on the class group, and thus it makes sense to talk about these gamma weighted zero-sum sequences. Because I mean, itself, the elements of the Galois group they are not endomorphisms of the class group by definition, but they're naturally associated. So, and so this result here, which we obtained, it's not entirely satisfying in a certain sense because the transfer homomorphism involves an arbitrary choice. Or put differently, the monoid here is not ideal because there's some redundancy there. For instance, I mean, if we take a cyclic group with 3 elements, for instance, and then we allow weights plus and minus 1, so a plus identity, minus identity, if I want to be strict with endomorphisms, then we could just as well more or less consider just the positive element, so to say, and 0, because I mean, whether I have plus or minus e, I can always adjust this with the weights. I just take the opposite way. I mean, the monoids, these two, they are not really isomorphic, but for questions of studying the arithmetic, they are the same. For instance, one could say one can take another transfer homomorphism from this monoid to this monoid. So in that sense, it's not ideal, this transfer homomorphism. And more generally, for any group, I can more or less replace G by any subset G0, such that G0 union the negative elements gives the full group. And more broadly, I could always take a representative of one orbit if I have a group operating on, if omega would be a group operating on G and so on. But in some sense, if one thinks about it, maybe just to try to stick to elements is not the right approach, because then, I mean, also, okay, if minus E, it's maybe more natural to write E than minus E, but I mean, here already I made an arbitrary choice, and which G0 to choose here and which element does one choose from the orbit. So why not look at it slightly differently? So if I have a sequence, then this sums omega IGI. So I said this is called an omega weighted sum. But so if you denote by capital omega of G, just the set of all omega G, omega, little omega and large omega, then I can just as well write this set here as a set, as a sum set of these elements here. And if I now just write AI for omega GI, then the condition that it's an omega weighted zero-sum sequence becomes that 0 is an element of this set, this sum set. And written like this, I just could say, well, there's a sequence AI, A1 up to AK of subset of G, and we call it a zero-sum sequence if 0 is an element of this subset. So why not formulate it in this way? And then I can generalize even further. So I forget where these sets came from, and I just say for whatever finite abelian group, I take a collection of subsets, and then I consider the free monoid generated by this collection of subsets, and then I consider sequences of subsets. And in fact, David Grinkiewicz used constructions like this to formalize the idea of set partitions, which is relevant in additive combinatorics to obtain certain addition theorems. So to really consider free monoids generated by subsets of a group. And so then here for some sequence S, now it's a sequence of sets. Then I say it's a zero-sum sequence if 0 is an element of this subset. And then I can, in the very same way, consider the submonoid of zero-sum sequences of sets. So, and then I can rephrase this result in the following way, that it's all the same, but here I now have the monoid of zero-sum sequences over the orbits themselves. So it's, in some sense, it's the same, but it's arguably more elegant because there's no arbitrary choice involved anymore. And so this is a motivation really to, an immediate motivation. This was the motivation for me to look at this concept, but now, I mean, the concept is there, one can now study these monoids also for their own sake. And maybe, so this was the first part of the talk. I also said there will be a second part, which gives some arithmetic results, but the time is relatively progressed. So the second part will be very brief, but still somehow to say what I wanted to say about these arithmetic results. I just, this I've already shown this. This is just a recall that we study number of vectors in the factorizations of elements, and one wants to understand those. And one way to start to understand them is to consider the unions of all lengths that contain a particular element. So this was a notion introduced by Chapman and Smith, maybe almost 30 years ago by now. So because this somehow smoothes out certain irregularities, so the structure of these sets is generally nicer than those of the sets of lengths themselves. And one then can study their maximum and minimum, and then the ratio of the largest and the smallest elements, and one calls these elasticities. And then one has also other concepts, but I will skip this because I won't arrive to discussing these notions. And now one wants to study these elements here, and then first the factorization of in these monoids. So the first thing to understand what are irreducible elements here, and the elements are irreducible. Well, if I cannot decompose them in such a way that 0 is a sum here and 0 is a sum here. And an important point here is, contrary to the case without weights, it's not sufficient to say that a sequence is reducible if it has a zero-sum sequence is reducible if it has a subsequence that is a zero-sum sequence, because so to say the co-divisor might not be a zero-sum subsequence. Because while 0 plus a equal to 0 implies, of course, that a is equal to 0, that 0 is an element of A1 and 0 is an element of the sum set A1 plus A2 does not at all imply that 0 is an element of A2. And in particular, this means that this monoid here is not a Krull monoid. And so in that sense, it's a different type of monoid than the other ones, which makes the problem interesting. And then one can show, and it's not too hard to do, is that these monoids are finitely generated, simply because one can establish a bound on the length of irreducible zero-sum sequences, and then as a consequence of the fact that they are finitely generated, one already gets an entire bunch of finiteness results. I will just focus on this part here, on the third one, which says that these sets UKH are almost arithmetical progressions. So this is an arithmetic progression, but at the beginning, at the start, there can be some terms missing. So it's an arithmetic progression, and at the beginning and at the start, one can skip some elements. And so this is a known result for finitely generated, any finitely generated monoid. So it's not really a new result, but it applies to this type of monoids. And yes, I will skip this. And then one can show that in this case, as well as in some other already known cases, but in particular also in this case, so one knows from the general theory that these sets here are almost arithmetic progressions, but indeed for this particular type of monoid, one can show that there are arithmetic progressions, and in fact, arithmetic progressions with difference 1. So which is somehow the best one can hope for. And the proof is similar to a proof of O, who showed the result for product 1 sequences, which would be the non-commutative version of this problem. And so there is the classical result for zero-sum sequences, which is of course also known. The more recent generalization of O to not necessarily commutative groups, and now we have the generalization for the situation with weight. So maybe one could also give a joint generalization, but so far nobody tried to do this. So this would be an open problem. And I think I will leave the other arithmetic results for another time, because I'm already towards the end of my time. So I thank you for your attention.
Thank you very much, Wolfgang.